Stefan, we wait 2 minutes because there are always some latecomers. So, very hot day, but relieved to see it's not as hot as I feared it could be in this room, which is facing east or northeast. Okay, 2 people have arrived, so we'll consider this is the contingent that we were waiting for, and we will start. So welcome everybody. Welcome everybody online as well. We are very fortunate to have Stefan Llewellyn Smith, who we learned a short while ago that he was coming to Paris. So I've known Stefan forever. He has worked on convective stability and instabilities for a long time. In fact, I met him first in Cambridge, UK, and he was already working on similar things. He then did a PhD with David Crichton, and then a postdoc with Bill Young, who I see is still here on the first page. And he has worked both on fundamental aspects of instabilities and also is a well-known user of Basilisk. And for all these reasons, we are quite happy to have the possibility of chatting with him. Please come see us after the seminar. I'm not sure how long Stefan can stay this afternoon, but he's in Paris most of the week, I think, right? So there's still a chance to connect with him. So without further ado, Stefan, please start.
D'accord. Ah, it's gone green now. Ah, green. Exciting. Can anyone hear me now? Good. All right. So I was just saying that we all understand Rayleigh-Bénard, right? I won't go back over that. Okay, so there's a lot of words here, but let's not worry about it. As I said, we have a conductive state, hot under cold. It goes unstable, and we normally measure how hard we force the system by this Rayleigh number, which gives us a measure of the forcing by the temperature difference, by the size of the system, and by the diffusion and viscosity that try to stop it. So we think about it mathematically as a parameter space with a marginal curve separating stable and unstable regions. When my Rayleigh number is high enough, I go unstable. And it turns out there's some very nice mathematical properties that happens. This instability happens with no oscillation. It's got zero real part to the growth rate. And there are lots of nice mathematical properties. Now, one thing I won't talk about, actually I'll mention it briefly, but not for Rayleigh-Bénard, is that if you imagine pushing the system very hard, it won't just be a linear instability. You'll have very intense motions, and there's a very large literature about appropriate scaling laws. If I push the system very hard and I measure its response, usually by the Nusselt number, how do those things scale? And that becomes quite a theological discussion. I won't go into that much. Now, you might say, well, this is not the only kind of stability problem that we know and love in hydrodynamics. The other classic problem is shear flow stability. So people talk about the Orr-Sommerfeld equation for shear flows, the Taylor-Goldstein equation for stratified shear flows, which if Colin Caulfield were here would tell me is the only sensible thing to listen to. And then we have Squire's theorem, which is another mathematical nice result that tells us I can look at 2D disturbances for some of these theorems. There's a whole bunch of lovely theorems for inviscid flows, Rayleigh, Fjordhoff, Miles-Howard, etc. And this is just to remind ourselves that we have a very extensive literature about hydrodynamic stability. And so some of that may or may not be useful as we proceed, and we'll see that. Okay, I'm going to work with these equations. For the program last week, we were told we had to put the equations up, so I did. So these are the Navier-Stokes incompressible Boussinesq equations. We have buoyancy as our temperature-like variable. It's simpler to use because the units are simple. I've rescaled pressure, and we see we basically have viscosity and density. And then for the mathematicians, I spoke about the boundary conditions. So the velocity boundary conditions are not too important for this discussion. What's quite important are the heat or the buoyancy boundary conditions. And I'll talk more about this. But you can think about either specifying the flux of heat through the boundary, which would be proportional to the vertical gradient of B or the normal gradient of B, if you prefer. Or you could specify forcing at a boundary. And we'll see that this is typical of horizontal convection, and that this is a very interesting thing to do, or to talk about the value of this gradient for the problems I'm interested in. Okay, so that's the equations. And so you might say, well, Rayleigh-Bénard's great, but the real world's more complicated. So here I've listed all the things you can do to go beyond Rayleigh-Bénard. So you could say, okay, I could change the way I force the system. It's not just hot and cold. I force it with some kind of periodic dependence. I force it by radiation. Imagine the sun shining on your water. Or I could force it at the surface or at the bottom mechanically with wind. I'll come back to that. or I could force it at the boundary with some kind of horizontal gradient, so I no longer have my hot, cold, or cold, hot, or whatever uniform boundaries. One thing I'm not going to talk about is having what happens with finite domains, but it turns out this is actually, of course, a very old problem. It goes back at least to Cormac, and before that, there's some very old bachelor papers about this. It's obviously relevant to real-world situations. I'm going to give a theoretical talk, so I'm going to hope that the boundaries don't matter. I actually have concerns about that, which I can come back to later. Then there's all kinds of more physics with porous media, with rough boundaries, with moisture, sometimes called rainy banal. I'm not going to talk about that. So my goal is to come to these various variations and talk about the competition between this horizontal convection and this Rayleigh Bénard convection. Okay, so what does this mean? So first I'll tell you about radiatively driven convection, which I'm not going to discuss, but it's so pretty I should at least mention it. This is the research vessel Blue Heron, which I was on. It's an old fishing boat. It's not very big for an oceanographic vessel. And this is data taken by my colleague Jay Austin from the lake. This is from May to July. This is in the middle of the lake, not near the shore. And what you see, these are temperatures at 30, 90, and 150 meters depth. So this is a deep lake. And you see that it's not very warm. It's in 1.5 and 3 degrees C. So I don't recommend swimming in Lake Superior at 30 meters depth without the right equipment. And what you see in this period, the ice has melted. So the ice melts sometime in March, April, which is pretty miserable. The ice has melted, and in the deep, it's about 3 and a bit degrees C. Near the surface, it's colder, which is a bit weird if you think about it. And at 90 meters, the temperature is oscillating up and down. This is at a mooring. So it's jiggling up and down. Eventually, you see that the top surface warms up, warms up, warms up. The sun is shining on it every day. Well, maybe not every day, but most of the day. And then eventually the temperatures meet up. They warm up, then they hit this number, and then they start to diverge. It stays cooler at depth, and it warms up near the surface. And this was at a specific mooring, which also shows these jiggles. So you could say, what on earth is going on? This makes absolutely no sense. We've got cold water at the top. We've got all these massive oscillations. It's warmer in the depth, and then it all does that. So what's happening is that the sun is shining on this lake in May, and it is shining on this water, and near the surface, that's 1.5 or 2 degrees. And as it does that, this water gets denser because we're near the critical weird point of water, which is densest at 4 degrees. And so the sun, by warming the water, is triggering convection that goes up and down and is mixing up the water column. So, and then eventually, as the water at the surface gets warmer, it starts to have this appropriate density profile. Here it's all homogenized, and here water is above 4 degrees. So now, of course, the hot stuff gets warmer at the top, and it stays colder at the bottom. So this is upside down convection driven by the nonlinear equation of state. So that's a fun problem, and it's not one I talk about, but I do like showing that slide because it's so surprising. This is a numerical simulation of horizontal convection, not carried out by Basilisk, I'm sorry. And so what happened here is you have this long, fairly long box, and we're imposing a non-uniform buoyancy at the surface. In this problem, it's cold in the middle, and it's warmer at the sides. And there's no buoyancy flux through the bottom. So the only way energy comes in is at the top, or heat. And this is a reasonably high Rayleigh number. You see it's a fairly complex flow. The flow is falling down at the bottom. It's doing things in a quasi-steady state. There's some kind of recirculation. And this is an old problem. It goes back to the early 20th century, a man called Sandstrom. And it's obviously a conceptual model of what's going on in geophysical systems. If I think about the Earth, well, I've got the ocean. It's heated at the equator and it's cooled at the poles, more or less, in terms of atmospheric and insular solar flux. And there's a very nice review by Griffiths and co-authors that talks about it. And there are some interesting mathematical and physical questions. So, for example, this calculation's got no buoyancy flux through the bottom. And if you work out the horizontal average, I'll show it later. If you work out the horizontal average of the flux, there's a convective flux and there's a diffusive flux. And that total flux is conserved in a statistical steady state. So if there's no flux through the bottom, there's no flux at any height. So whatever is going up must be coming down, which means that you can't talk about the Nusselt number as how much heat's coming out of the system, because there must be zero heat coming out of the system. So you have to think about a different definition of the Nusselt number. So that's what I said here. Okay. So that is horizontal convection, effectively, in a nutshell. And I had a student who did some experiments on this. This was to try and look at mechanical forcing at the surface and a buoyancy forcing to see the competition between them. Yet again, this question about competition between different kinds of forcing. And these experiments are long and fairly painful because you're either doing it with heat, in which case you have to insulate your tank. So if you're putting foam and stuff, you have bad optical access. Or you're doing it with salinity, with salt, in which case your Schmidt number is wrong, everything is very slow, and you can't, you have to have a balance of the salt coming into the system. So she did PIV, she looked at the circulation. You can describe it by a recirculating box model. I'm not going to talk about that. My main reason to show this was to point out that it's quite painful. So I'm going to go back to theory, which is less painful. There are some experiments being done at the moment by a group in China, doing long-term slow experiments of these kind of convective flows. And what they've done is they've put effectively a thermos, an aquarium, or not aquarium, a tank, which has insulated walls with vacuum gaps between them to stop the heat fluxes messing up your long-term statistics. Okay, so let's talk a bit more about horizontal convection. This is a snapshot of the stream function. This is a 2D simulation of the buoyancy. So as you see, the buoyancy in the abyss is really boring. This is zoomed into a boundary layer. The abyss becomes cold. It fills up with cold fluid. Okay? There's actually a weak stratification that you can't really see. And there is a boundary layer at the top, which has a stable stratification as well. Depends where you are, right? Warmer here, colder here, but effectively it's stably stratified under the warm regions. As I said, there's a question about what the Nusselt number is. And it turns out that some of the definitions are problematic. You have to make artificial definitions to get a non-zero number. So I will strongly advocate this definition of a Nusselt number. So it's related to the dissipation of buoyancy variance. So this is my buoyancy variance grad B squared with a kappa in front. That is chi. Lou Howard showed a long time ago that this can be related to entropy production. And you can define a Nusselt number as this chi divided by the chi you would get in a purely diffusive solution. So the idea is a bit like in Rayleigh-Bénard. Rayleigh-Bénard said the Nusselt number is my heat flux divided by my conductive heat flux, which solves your Laplace or Poisson diffusive steady solution. Similar idea, you work out the buoyancy variance and divide it by what you would get with a purely diffusive solution. And so people do work on scaling laws. I think I mentioned it, but that's not the goal of this talk. So this is just mathematically, again, for the IHP group. So this is what I said, that if I average in the horizontal, this is the total heat flux. There's a convective part, WB bar, and there's a diffusive part. What's particularly interesting in horizontal convection is that you can relate this object, which is the average of WB over your entire domain, with the power dissipation, the rate of dissipation. So if you're interested in how energy is partitioned and moving through your system, you have a very strong constraint that in a statistically steady state, the conversion between potential and kinetic energy is the same as the rate of dissipation of kinetic energy. And so last week we had talks about that, and a particular column was talking about it. And with this result, you can put a bound on this object epsilon for horizontal convection. B star is a maximum value of the buoyancy at your surface or wherever you're applying buoyancy, kappa and h to depth. This is, of course, dimensionally correct. And this leads to what is sometimes called an anti-turbulence theorem, which says that in some measures, if you have a constant Prandtl number and you increase the Reynolds number or the Rayleigh number, you can't have turbulence in one of these systems. I'm not going to go into that. That caused a bit of fuss about 20 years ago. I'll view this as a bound on energy dissipation and on conversion from potential to kinetic energy. Okay, and so while I said I wouldn't speak about bounds, it is useful to know that the bound in horizontal convection with that Nusselt number goes like Nusselt less than rate of the third. That's the mathematical bound. Turns out that in practice, in numerical simulations, you don't see 1/3, you see 1/5, maybe a quarter. There's some debate about that. The 1/5 scaling goes back to Rossby, to experiments back in the late 60s. It's extremely robust. You see it actually both in experiments. You can also conceptualize it in terms of a number of balances, dominant balances, and let's say a vorticity balance. And all the balances give 1/5, which makes you worry about 1/3 or 1/4. That number C, I play games with it. You can get it down to quite a low number. I won't talk about that. There's also a paper by Shishkina and Grossman or Schumacher, I've forgotten, which has a whole zoology of different possible scaling laws depending on your Prandtl and your Rayleigh number. I won't talk about that. Okay, so let's talk about the main goal of this paper, this seminar, the competition between horizontal and Rayleigh-Bénard convection. So these are some results by a paper that's been accepted, should be out soon. And so this is some more background. And so this is the question, okay, imagine that I have a system which has both a horizontal convection-like forcing, so there's one boundary which has some modulation, but also Rayleigh-Bénard convection, so I'm also driving it at one of the boundaries by either a temperature difference or a heat flux. So what's it going to be? Is it going to be Rayleigh-Bénard-like? Is it going to be horizontal convection-like? And so one thing we have to think about is how do you measure that? So one thing you see is that in Rayleigh-Bénard, as I increase the Rayleigh number and push it harder and harder, the flow starts to basically mix up quite well in the interior. I mean, that's a statistical sense. There may be individual plumes and blobs and whatever that are moving heat around. But if I take some long-term average, fuzzy average, it becomes well mixed in the interior with boundary layers. And the boundary layers are one reason why people argue about Rayleigh to the 1/3, 1/2 optimal regime. So I'm not going to talk about that. Whereas horizontal convection, I showed you a picture. You could see that actually the color scale was not very good. But it turns out that if you average this over the whole domain, it's stably stratified. It's not obvious. There we go. So this is calculation to understand when do I get things that look like Rayleigh-Bénard, when do I get things that look like horizontal convection. And so this comes from numerical calculation at reasonably large Rayleigh numbers. They are 2D calculations, which doesn't appear to be the problem in this line of work. One thing I'll note is the Prandtl number is 0.7 for air, 7 for water at standard temperature and pressure, more like 10, 12, 13 for colder water. And we'll see why that's relevant later. A number of our results are Prandtl's 1, right? Because that's the simplest thing to write down. But it's important to think about what happens for other Prandtl numbers. Okay, so the following slides I borrowed from Florian. And they sort of give some motivation for this problem. Okay, so here's a paradox. Imagine that you look at the Earth's ocean and you look at the bottom of the ocean. So the Earth's ocean is about 4 kilometers deep on average. And at the bottom, there is a small flux of heat through the base. It's about 50 milliwatts per square meter. And you can look that up. Geophysicists get very excited about this. And it's higher near mid-ocean ridges, and it's cold in other places. And you can build a Rayleigh number. Now, you have to be careful because your Rayleigh number is a flux-based Rayleigh number. Which means it has an h to the 4th over here, but we can do that. And you plug in all the usual values for water, 1,000 kilograms per cubic meter, whatever Cp is, mu, kappa. These are molecular values, of course. And you get 10 to 24. That's a pretty big number. But the Earth's ocean is not well mixed by Rayleigh-Bénard convection, not at all. The Earth's ocean is stably stratified. It has a complicated density structure. It has a thermocline in most places, so there are differences in the gradient. And this calculation is terrible, right? It doesn't tell you what happens in the world ocean, but it's very counterintuitive because it's such an enormous number. So the real problem is that you need to think about rotation, wind, tide, salinity, all these effects, and horizontal convection. So one of the questions here is we need to be careful just about saying Rayleigh numbers without thinking about what effect is physically dominant. And here's another motivation, which is the one that really is driving kind of the setup of these numerical experiments. So this is one of the icy moons in the solar system. This is Enceladus, but what I'm talking about is relevant to the other icy moons, which have the structure of a rocky core, an ice shell, no, sorry, the ice shell is this thing, and a global ocean. Okay, and we know these things exist based on various measurements from planetary missions. Enceladus in particular has these jets of stuff coming out near the South Pole. People have measured what's in that. It's mostly water with interesting other bits. And so the conception that we have is an ocean with a rocky core under, ice shell, and the rocky core is going to be producing heat, right? For a number of reasons. First of all, there's radiogenic decay, just like in the Earth's core. but also these are satellites of large planets with large magnetic fields, so they're being crushed around by tidal forces, which are generating heat in the core. And then the ice sheet, we are told, I don't know how they measure this, that the ice sheet's not of constant thickness. And so when there are regions where the ice sheet is thicker or thinner, then effectively think about the mass of ice lying above any point. By Clausius-Clapeyron thermodynamics things, it'll change the freezing point of the water. And so the water we expect to be freezing just next to the ice sheet, otherwise there'd be some flux. These are quasi-steady states, we assume. And therefore we anticipate a variation of thickness leading to a variation of temperature at the top. So there's a simple conceptual model that I have flux through the bottom and I have a temperature variation at the surface. So it's my competition between my horizontal convection and my Rayleigh-Bénard type convection. And the question as to what you see is quite important, because whether this ocean is well mixed, as in Rayleigh-Bénard, or horizontally stratified, has big possible consequences for what sort of flows you will see in the ocean. And this is not an obvious answer, because if you look at the literature, you'll find papers about this, and in one paper they'll say, oh, the ocean's well mixed, and we do blah, 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 blah. The next page they say, oh, the ocean's stably stratified, and we do blah, 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 right? And so these are the same people, by the way, a year apart. So there's a real question as to what's going on. So this was a simple conceptual paper to try and understand what happens. So these are the results of these 2D numerical experiments. And you take a vertical Rayleigh number. So that's how hard am I pushing Rayleigh-Bénard, how much flux is coming through the bottom. And I got a horizontal Rayleigh number, which is how hard am I forcing my variation in buoyancy at the surface. And if you think about it, if my horizontal Rayleigh number is 0 and I'm down here, I've just got Rayleigh-Bénard, it's going to be all nicely homogenized in my simulations, provided this is big enough, right? I had to be above some stability barrier. And if this guy is 0 and I'm over here, I got horizontal convection, I drive flow, I expect to get stable stratification. And what Florian found is a very nice set of scaling laws that separate this Rayleigh-Bénard type regime with this horizontal convection type regime, and there's a transition from a Rayleigh 1/2 regime here, which is fairly well documented, and a Rayleigh 4/5 regime, which is not obvious when you first start this. The different color symbols are different aspect ratios. So you see it's independent of the aspect ratio effectively. Maybe there's a slight rescaling of the curves, but the behavior, the scaling law, seems to be independent of it. This is a compensator plot to show the 4/5 regime as you get high enough. But I should point out this is just Prandtl number 1. So we definitely see this variation in our two stratifications, power law behavior, and an aspect ratio independence. I should be very clear though, one thing that's important to note is that this Rayleigh number here is constructed with the depth of the ocean. You have to be very careful because the literature for horizontal convection often talks about a Rayleigh number constructed with a horizontal length scale. The argument there being, well, what's important is over how much horizontal variation am I driving a flux, a gradient of buoyancy. It appears that actually what's important is that kind of Rayleigh number. That's the depth that matters, not the length, as you can see from that plot. And although I won't show it, Florian found explanations based on scalings, the equations for these different 1/2 and 4/5 scalings. So that was nice. All right. Now this is what I want to talk about. This is the main topic of the seminar. The rest was just an introduction. So let's talk about the stability problem. And sometimes you'll hear people say, oh, horizontal convection's got no basic state. What do they mean by that? What they mean by that is if I have a variation of buoyancy at one of the surfaces, and I look and I think about there being a state of rest, because that's what I have in Rayleigh-Bénard convection, I got a conductive state, no motion. If I try and imagine a state of rest with a buoyancy gradient at the surface, it doesn't work, because you look at the pressure gradients just below it, they want to drive flow. However, there are solutions that have no time dependence and a very simple structure, but they're shear flows. Okay? So you might say, well, what about these shear flows? They must be related to the stability of the system. And I mentioned these old papers by Cormack. It's actually Cormack, Leal, and Imberger. There are 3 papers. And in those Cormack papers, they're looking at the steady state flow inside a long enclosure. So there was a shear flow that appeared to be, for a small enough Rayleigh number, a nonlinear, well, who knows it's nonlinear, but a steady solution to the problem. So then you might say, well, this is a problem because if I look at my simulations, this is a typical example. It's a complete mess, right? There's no way I can do linear stability of that. It varies in the horizontal. But in fact, it's because this simulation has a boundary profile at the top that's cosine kx or something like that. Just in the box, it goes warm, cold, and warm again. You can't, that's very difficult. You get flow K, you get a mess. However, good news, it turns out that there's a very nice exact solution. And maybe this should be physically obvious. If you write the buoyancy as a horizontal term alone, and then a vertical variation, you can solve the equations. Maybe it should be obvious to us all. And what I'm going to do is say that I have this kind of buoyancy. This buoyancy has no vertical gradient, so it's not fluxing heat through the bottom. This term B is going to have some kind of flux coming in through the bottom. And then at the surface, if I look at this, if I make this guy vanish at the top, then at the surface I've got A1x. I've got a situation in my basic state where I've got a flux of heat into my system, and I've got a nice horizontal buoyancy gradient at the top. So that's really your canonical mixed configuration. And then you pick whatever boundary conditions you like for velocity. I'm not going to worry about that. You stick it in, you say I've got a shear flow, UV0, buoyancy, this is nonsense, this is A1x. And then you get this solution. Very simple solution, it's just in one direction. You get a shear flow driven by A1, driven by the horizontal buoyancy gradient, and you get a structure for the buoyancy gradient in the vertical, driven by the horizontal buoyancy gradient, I meant to say. And then this bit over here, its vertical gradient has F at the bottom, that's your flux in, and then a response G. You can work all these out as a polynomial, so it's quite simple. And then, of course, you can also cool at the bottom rather than heating at the bottom. So if I cool at the bottom, I'm making it more stable. You can have negative Rayleigh vertical. If you make A1 negative, you can see you can flip the system around. Doesn't change this, right? This thing goes like A1 squared, so that having a gradient this way is the same as having a gradient that way, which is kind of reasonable. You wouldn't expect the direction of your buoyancy gradient to change your vertical flux profile. And so then the question becomes, is this stable? This is the simplest possible thing. I don't want to go to Rayleigh number 10 to the 14 or whatever it was, 10 to the 12. I just want to understand linear stability. Linear stability is great. Let's see if I can do linear stability. I mean, Rayleigh and Bernard did it, and it went well for them. Well, actually, it's Rayleigh who did it, did the mathematics anyway. And the good news about this is that all this stuff doesn't depend on x and y. So I got Fourier transforms. I got an ODE. It's all great, right? And then you say, well, is this stable or not? What's rather interesting is that this function here, g, is always positive with this minus f term. So if this function is always positive, then the buoyancy gradient b prime is always positive. And so buoyancy is going up as I go up. And so you'd imagine that would mean it's always stable. But this is a problem because I can't just say, oh, my flow, it's cold at the bottom, warm at the top, therefore it's stable, because I got this horizontal flow. We know that shear flows can be unstable. And plus I got viscosity and diffusion, and we know there are systems where diffusion can destabilize a basic state. So we have an interesting question, is it stable or not? And it's a 1D problem, so we're feeling pretty good about our chances here. Now, of course, this isn't new. We didn't suddenly invent something out of nowhere. So let's think about the non-dimensional parameters and who's looked at this before. So we've got 4 non-dimensional parameters. That's actually, yeah, in this system, that's correct. We've got horizontal Rayleigh number, so how hard I'm pushing it in the horizontal at the surface. Vertical Rayleigh number, how hard I'm pushing it at the bottom. A Prandtl number, which is a property. There's also a parameter t, which effectively is a horizontal transport. It turns out in this system, you can have an arbitrary horizontal transport at any location. It can't change, but it's any location. That's non-dimensional. And so we're obviously going to take this to be 0, right? Because if I think about the real world, I'm going to have sidewalls somewhere far enough. So I'm going to assume that that's 0. And so these ideas go back to Hart, who did experiments for an MS and PhD thesis at MIT, and further experiments and some numerics later on at Colorado. And there are some nice papers by Weber, who was from, I think, the Norwegian Met Office. He worked on that in the 70s. And Weber actually had different boundary conditions. He had fixed buoyancy at the bottom. And we'll see this makes a difference. And of course, he was working in the 70s, so he did some numerics. And you have to admire the way he used, 16 Galerkin modes or whatever to be able to do it. But we got a bit beyond that. Okay, so one thing we'll point out is a very nice discussion by Kelly about what happens if you add shear to your standard Rayleigh-Bénard thermal convection type idea. It's well worth reading this paper. And now the thing you have to be careful about is that shear, Kelly is just adding shear. He says, okay, I can add shear. It's like putting in a body force. In our case, the shear comes out of my basic state. So if you look at this thing here, I got shear in the horizontal. The gradient of this object is not arbitrary. It's proportional to my horizontal gradient of buoyancy. So you can't just say, oh, I add buoyancy, it does this, because in our case, they're related. Nevertheless, the Kelly paper is very useful. And we discovered, this came slightly later, that there's an enormous strand of literature in the material sciences context and also applied math, and they call it inclined convection, and they're basically doing the Weber problem. So with fixed buoyancy, top and bottom, and their interest is materials processing on liquid metals, or at least they say it is, so they get very excited about Prandtl number 0.1 and 0.24 and things like that. There's a recent paper, well, fairly recent paper by Ortiz Perez and Davalo Orozco, who considered 2D solutions, and they considered 3D solutions, but only when they branched off 2D solutions. So that's a bit worrying because it's not obvious that those 3D solutions will be the most unstable or not. They may have missed solutions, and they got different boundary conditions. All right, so what happens in our problem? Okay, so you got a great intern, and you give him the equations. So these are the equations we give him. These are our Buoyancy equations, linearized about my basic state, capital U and capital B, which is here. And if you play games with Rayleigh-Bénard or with Orr-Sommerfeld, or Taylor-Goldstein, you will recognize these immediately because they look just like Taylor-Goldstein. Well, Taylor-Goldstein's inviscid, they look like viscous Taylor-Goldstein or Orr-Sommerfeld's stratification. I've got my three momentum equations, I've got my compressibility condition, I've got my buoyancy equation. I've taken a nice Fourier transform in the horizontal, and then my L operator is my vertical derivatives, which you could write as a capital D if you want, and my horizontal wave numbers. And because all the coefficients are time independent, x, y independent, I've got a growth rate sigma. So this is a set of ODEs. And the thing that is difficult is this term. This term is a problem. This term comes from the horizontal buoyancy gradient. If I didn't have this, these are the same equations we solve for every type of Rayleigh-Bénard problem. It's just that in Rayleigh-Bénard, Bz is a constant. In our case, it's a polynomial. This term here breaks everything. It breaks the Squires theorem stuff you had in Orr-Sommerfeld, and it breaks exchange stabilities you had in Rayleigh-Bénard. So you can't say that sigma is 0. You can't say that disturbances are 2D. You have to look at the full problem. But you start off with simple things. So this was saying, okay, let's understand what happens if I take 2D disturbances with no wave number in the L direction, the Y direction going into the board. And these are our first calculations. So you take a horizontal Rayleigh number and a vertical Rayleigh number, which is, I'm afraid, flipped around from what we did before, but never mind. And so if you start off with a 0 horizontal Rayleigh number, you got some weird version of Rayleigh-Bénard where you fix the buoyancy at the top and you fix the buoyancy flux at the bottom. If you do that, you can work out that you have a Rayleigh number of about 1300 and a K of 2.5. So it's very similar to our standard Rayleigh-Bénard. It's just got a slightly different set of numbers. And that's got exchange of stabilities. That's got everything nice that you like. So then what you say, well, what you notice in this case is it's a well-known result. This is Prandtl independent. Rayleigh-Bénard marginal stability does not depend on your Prandtl. So these different curves are different Prandtl numbers. They all come in to 1200 with this wave number, 0 frequency, and whatever, 1290. So then what you do is you increase your horizontal Rayleigh number, and you say what happens. And what you find is this is the marginal stability curve. So over here I'm stable, here I'm unstable. I increase my horizontal number. Nothing happens, and suddenly it crashes down. I stopped here, but it goes like that, completely vertical. So if your Prandtl number is small enough, 0.01, 0.145, 0.1, then the stability boundary crosses this axis. So effectively, if you have large enough horizontal buoyancy gradients, you're unstable, even if your flux at the bottom is 0, or even if your flux at the bottom is negative and you're stabilizing through the bottom. I haven't shown it, but these curves basically become vertical. But if your Prandtl number is big, so, you know, what have I got here? I've got 1, I've got a 6th, then it seems to go up forever. So then your system will never be completely destabilized by horizontal Rayleigh numbers. It'll just be unstable when you force it hard enough at the bottom. There seems to be a distinction with these Prandtl numbers. There appears to be some critical Prandtl number which differentiates between your systems that are destabilized by horizontal convections and systems that are never destabilized by horizontal convection. And the critical number is somewhere near a 6th, it appears, in this problem. You see that your wave numbers oscillate a bit. This one goes a bit crazy. It suggests maybe there's some kind of large wave, small wave number business here. It's not very clear. And you see that you do develop non-zero oscillations, non-zero frequency of your most unstable mode. You can't tell it here, but as soon as you're off here, you've got a non-zero but very small frequency. Okay, so we did that and we thought, okay, so there's a story to tell here. And so you say, right, Kelly said as I increase the shear, I increase the critical Rayleigh number. Does that happen here? Yeah, sort of. As I increase the shear, I increase this Rayleigh number. So that works for this. It doesn't work for these guys that come back down to 0. So that's a bit worrying. And then you could say, well, we could work out a Richardson number, which comes from our nice inviscid ideas about Miles Howard and Taylor Goldstein. You work out your Richardson number, you go through some algebra, find it's a polynomial h times the Prandtl number, which isn't obvious when you first do that. And so the Miles Howard theorem says you're stable for Richardson greater than a quarter. Turns out that h has a minimum of 3 halves. Do the algebra. It suggests that you expect instability less than a 6th, and you feel really good, right? You've got a reason why it's 1/6, and that seems okay. The problem is when you do this more carefully, life is more complicated, because what we have is we have our 3 different parameters, Rayleigh, Rayleigh, Prandtl. We have 2 wave numbers k and l. What we're trying to do is work out if I take any value of these 3 parameters and I find the most unstable mode over all the KL, what is the resulting manifold, or whatever you want to call it, in this 3-dimensional parameter space. These are better results. These are the modes I just showed you. They got L equals 0. You can call them transverse modes because this is the direction of my basic flow. So they have cells that look like this. And this is just what I showed you before, slightly more carefully done. You see that it comes down for Rayleigh numbers less than a 6, although a 6 seems to go up. The frequency goes actually slightly crazy, and the wave number doesn't do very much at all. I've cut these off when it goes down to minus 1,000. Stop these curves. Silly. But if I look at the other modes, which have 0 wave number along the basic flow, so they got things like rolls. So these are longitudinal, they're not quite the same. They have the same structure that as I increase my Prandtl number, I find eventually a region where the curve crashes down, so I become unstable to horizontal convection. And also for large enough Prandtl number, they keep going up. But we see some differences. So first of all, the frequency here is always 0. Then it jumps. It actually does jump. And you can see that here. The wave number is nice and smooth, then it jumps. So what does this mean? It doesn't mean I don't have enough resolution. I need to see the curve transition smoothly. It means that we have different families of unstable modes which are crossing in a complicated parameter space, and I'm projecting it down and seeing which one becomes unstable. So over here, these are instabilities that have 0 frequency. Let's say this purple one. There's the purple one. And then at this point here, whatever that is, somewhere in the hundreds, it jumps down to a different mode that has a non-zero frequency. And you can see these jumps everywhere. So the longitudinal instabilities are different. And we have a reflection symmetry, and that tells you that if this mode exists, so does its complex conjugate. So that's natural. So in fact, this is what's going on. So the issue is that we have a parameter space that's more complicated. These are the transverse modes. This is horizontal vertical Rayleigh number. This is the vertical Rayleigh number. This is the horizontal wave number. And so what we're actually seeing is the projection of a 3D manifold down onto the surface. And so you can see that for small Prandtl number, there's a barrier here. This is Rayleigh-Bénard. There's a barrier here. This is where your horizontal forcing makes you go unstable. And then this surface connects in a funny way. And then this region here, this kind of slightly cut off region, this region here, you're seeing it projected down. But as you increase your Prandtl number here to here to here to here, you completely lose this. And so you only have instability in a kind of convective type setup. You lose this horizontal instability. Or maybe you don't. Does this go away to infinity or does it just vanish completely? That's the real question at the moment. So those are the transverse modes. These are longitudinal. The same basic idea. Here's your Rayleigh-Bénard. Here's your horizontal instability. You do see a difference that there's this very uniform in Rayleigh X barrier. See that you split off two different families of modes here. They're clearly different physics. These guys is getting shrunk down, so it's not clear if this vanishes or becomes infinitely thin. This guy keeps moving away. This is 0.01, 0.106, 0.2. So you see, in fact, 1/6 is not really the limit, because this is above 1/6, and you still have an instability here. So 1/6 is not entirely convincing. And in fact, 1/6 should not be relevant to this problem, because 1/6 should be relevant to transverse modes, because it's a sort of Taylor-Goldstein type argument. This is the horizontal Rayleigh number, logarithmic scale, 10, is it 1, 10, 100, 10 to the 5. So this thing here is moving away, but you don't know if it's going away forever or if it's vanishing. And then for large Prandtl number, and by the way, this is 0.7, so this is air. All this zoo of good stuff is for small Prandtl number, right? So it's completely not relevant for water or cold water, unless this thing here survives but moves away. But at least there's serious questions about what happens in environments where your vertical Rayleigh number is 0 and your horizontal Rayleigh number is large. It's not clear what's going on. Now, I suspect that in any of our real-world applications, the horizontal Rayleigh number is way up here, right? So this is all worrying about nothing, because you're clearly unstable convectively, unless I guess you're freezing your core. This is what the modes look like. This is Rayleigh Z equals 0. So this is along this horizontal axis. These are marginally unstable, so their Prandtl number must be small enough. I've forgotten what I used. So what it used? There we go. Prandtl number is 0.1. So my horizontal Rayleigh number is 13,000. I don't know what this, and this is Prandtl number is 1. Yes, so I can find unstable modes for Prandtl is 1. It's just that the Rayleigh number is very large. And what you find, this is UVW P and B, with also 0 for reference. You find that as I do this, these modes are increasingly hydrostatic. They're dominated by a balance between buoyancy and vertical pressure gradient, which is completely different from Rayleigh-Bénard, which is not at all hydrostatic. And they're also concentrated near the low boundary. You can see all the action is down here. You can see your nice BDX coming down to 0 here. No flux of heat through the bottom. So you can try and do asymptotics. That's what I do for a living until people stop believing in asymptotics. There's a scaling for large Rayleigh and small L. That's over here. Large Rayleigh, small L. Going over here, I'm staying close to the boundary. If you do that, it turns out you can real scale the equations and you get a different set of equations. That's hydrostatic. And we can solve these numerically, but they're the same equation set as before, just losing this left-hand side. Turns out the good news is, when you first see these equations, you go, oh my goodness, this is bad, 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 because I've lost the viscous term on the right-hand side, and therefore it's going to break all of my solvers, because they'll expect viscous terms everywhere. But it's okay, you don't need this viscous term. If you think about this as a shooting problem, you see that actually that's completely irrelevant. The only viscous terms you need are the shear terms. So you can solve that, but it's not clear it's going to give us everything new. What you also see is that in this non-dimensional version, and I should have shown it before, clearly there's, in the W term, which is the buoyancy gradient in the vertical, you can see a vertical Rayleigh number and a horizontal Rayleigh number squared. So that was implicit in my initial discussion of the equations. Where was it? Here we go. This is A1, which which is Rayleigh sub x, a1 squared, this is Rayleigh z. So you expect that there's some balance between Rayleigh squared x and Rayleigh z. And that, in fact, is the scaling at the top. That curve going up is exactly that scaling that you expect. The other question, and I'm going to sort of come to a halt pretty soon, is what about this thing that seems to be moving away to infinity? So the pure horizontal Rayleigh number with increasing Prandtl. So I show you here 0.2, 0.5 and 0.7 I don't show, but in fact that curve still exists. It's just a long way further to the right. And so you can try and do some kind of analysis for that. And this shows you what the problem is. So you can try and increase your Prandtl number. So these are different Prandtl numbers. I forgot to write down what they were. What this is showing is as you increase the Prandtl number, the Prandtl number is changing as I do this, and you're seeing the resulting critical Rayleigh number and real and imaginary parts. So what you want is these guys to be 0, because you can convince yourself this must be a solution that has no frequency in it. And you see that, you know, as you increase your thing, your Rayleigh number increases, it's all pretty reliable. And then when you get to here, it becomes totally unreliable. Things start to jump. Your numerical eigenvalue solver is struggling terribly. And if you do that, you believe the numerics, you can show that there's an exponential growth in the critical Rayleigh number with Prandtl number. I have no idea what that means physically. And the thing that's most surprising is that with the material processing case with fixed buoyancy, as you increase your Prandtl number, you saturate to a fixed value of Rayleigh x, which is about 13,700. So if they did it, they've got all their numerics, it works fine. In our case, our numerics are falling over because we have large terms and small terms, and there's just, you have to do it in quadruple precision or, you know, super high precision to believe your answer. So the last thing I'll say here, this is the very depressing thing, is, well, very depressing, I don't know. It's worrying me. I showed you this surface here. You see it's very insensitive to this Rayleigh sub vertical. You also see that my flow is very hydrostatic, concentrated in the boundary layer. So I tried a boundary layer scaling. Where is it? Here it is. So, okay, well, there's not much dependence on Rayleigh y and L, so you can do this. And you can do a boundary layer scaling. So if you take a stationary mode with k and sigma both 0, that's the exact equation at the top for the vertical velocity, right boundary conditions. So if you're in this regime, so large horizontal Rayleigh number, but you're not in the convectively unstable zone with very large vertical Rayleigh numbers, you get a two-term balance in the interior, which you can solve numerically. Near the boundary, there's a boundary layer. You can work out the scaling. Find there's a boundary layer, there's a Rayleigh scaling in front of Z. Find the scaling is 1/4, which I forgot to write down. You can see you're balancing Rayleigh to the 8 alpha with squared. So alpha is 1/4. And you get these boundary layer equations, which are an 8th order boundary equation. And the amazing thing is you can solve that analytically, or you can write down a solution based on Paris, 1980. Paris was an asymptotics person, a Scottish guy did asymptotics who spent some time in Paris. Paris, the city, well, Saclay. He wrote these papers about these boundary layer calculations. And so then you can work out 2 boundary layers, match the interior. I've done all that, and I don't know if it works because I haven't been able to convince myself that the resulting nonlinear equation is solvable. All right, I'm going to finish up. This is just talking. I'm going to skip that. Well, I'm going to talk very briefly. So one thing you can do is you can say, okay, what if I try and rescale this? It turns out the scaling we used is not very convenient to think about these families of modes. Large Rayleigh number, that's the correct scaling in terms of a Reynolds number, in terms of a ratio of Rayleigh numbers. This is typical, as I said before, RAZ over RAX squared. And if you do that, you can formally remove some of the diffusive terms. Because you say, okay, I rescale this, and effectively, this term becomes large, this term becomes large. If you play games with that, you can get a set of equations that does have Square's transformation. The Prandtl number has to be large enough for this. If you do that, you can convince yourself by writing down what effectively is a Taylor-Goldstein equation, that there are a certain number of modes. So this is, in a way, slightly ad hoc because we've decided that we can analyze them by similarity. We're working in a large Rayleigh regime and writing down results from it. But you can find instability near the boundaries because the Richard number is locally small or you're convectively unstable. And this region is narrow, so you expect to stabilize that with viscosity for the Richard number. You may get critical layers. That's a problem. You may be globally convectively unstable, which is the result I showed you. And right at the middle, you have a shear flow instability. The Prandtl number is less than 6. So you do recover your naive guess, and you find the different families of solutions. And all of those families of solutions you can relate to the behavior of these marginal surfaces as you go to large Rayleigh number. But it's still not telling us exactly what's happening here. So in fact, we do have a fairly good understanding of the physics of the different modes, which I'm afraid I glossed over because it took me a bit of time to get there. And the longitudinal modes, you can actually derive an extended Taylor-Goldstein equation. So the next step is to make sure that this equation is consistent with the physics I've told you. So I'm going to try and stop now because I've gone slightly longer than I planned. Okay, so this, I gave you a lot of background, but this was on trying to understand the simplest horizontal convection linear stability problem. For large Prandtl number, it's an issue numerically, we've discovered. Our asymptotics don't quite work yet, but we have been able to get physical insights from the large Reynolds number scaling. So we have convective modes, central shear modes, boundary shear modes that we don't think are going to survive. And then what I didn't discuss, there are also 3D baroclinic modes. There are modes that have to have the horizontal buoyancy gradient as well as the vertical shear. And those are similar to modes that have been seen in previous papers in the last couple of years. Now, so one question is pure horizontal convection stable. What about this Taylor-Goldstein equation? Now, if you're feeling very enthusiastic, you can add rotation. That's actually, you can add to the basic state. All right, so I'll skip. I think I'm going to stop here. I'm sorry, I slightly had to compress the end of it, but I'm happy to take questions. Sure.
So thank you for this fascinating view of natural convection, Rayleigh-Bénard convection, horizontal convection, etc. Now we are open for questions. Who has questions? Yes, Laurette.
Wait, the microphone. And it's for the online people.
Well, hello, online people. I come, like most people that we know, primarily from Rayleigh-Bénard world, but I studied natural convection in these last couple of years with a group of Tobias Schneider and Zheng Zheng. And so I had to learn all about it. And the main thing I learned, and I wrote in the introduction, you see, I know it so superficially that I'm reading now what I wrote.
Right.
And the big distinction seemed to be between what they called the diffusive regime, the conductive regime and the double boundary layer regime. And this was a distinction that was put forth by the great master Batchelor. And in one case, this is not geophysical, but you're imagining something with top and bottom boundaries. And if you're going to idealize it in this way, homogeneous here, the idea is when can an idealized periodic boundary condition problem in a vertical direction, when does that resemble the inner part of something that has a top and bottom boundary? And that is bounded by, has to do with, of course, the height, but also the Rayleigh number. And that was, in all the things I read, that was a huge deal, was in vertical convection, are we in the double boundary layer regime or are we in the conductive regime? And the people that I was reading was Batchelor, Eckert and Carlson, Gill, Vest and Arpag, Mizujima, Goto, Kimura, Bejan, Le Quéré, and I don't see any of that here. So what's the difference?
Okay, so I briefly mentioned the work by Cormac, which was with Imberger and Gill. So that was partly inspired by this original Batchelor and Gill papers. Now, if you read the bachelor paper, it's almost incomprehensible to modern eyes because it's written before we develop a lot of the usual terminology. So there is a strand of literature about these tall enclosures, and yeah, that's right, that's the bachelor paper. And we have not made much of a connection because in most of the situations we care about, these are very long systems. And so when I show you simulations that are, most boxes are at least 4 by 1, and then I think Florian's been up to 32 and 64 by 1. I have to go back a bit. Right, so you see his boxes are 8, 16, 32, whatever. So geometrically we're different, and in that the physics is different. However, the question about what do the ends do to the flow is something I worry about, especially for these kind of stability problems, because if you work out some great stability result and you're super happy about it, but in fact everything goes nuts at the boundaries and that's where it goes unstable, what have you learned? And when I talk about the baroclinic modes here in the conclusion, so I slightly skimmed over them, and most of that was complaining because, wait, it's in the conclusions, isn't it? Yeah, here we go. Because, for example, this paper by the OPDO paper, I called it, which looked at 2D calculations, and then it looked at each 2D marginal mode and said, does it become more unstable if you go and become 3D? It doesn't do the whole 3D surface. The problem with those is that it's entirely unclear whether these baroclinic modes appear spontaneously or bifurcate away. You'll be able to tell me maybe if they can bifurcate away from, if they have to bifurcate away from the boundaries. Whereas there's a previous paper by Rhin et al. Where the most unstable modes are clearly 3D perturbations near the boundary. So the question of whether your boundary is critical for your total flow evolution is non-trivial even if your boxes are super long. So the answer is that, yeah, I'm aware of some of that strand of literature. We haven't made a comparison to it, but the underlying philosophical question is relevant.
But the main point is that
their things are tall.
And I was talking about
well, that's what they're modeling windows, right? Windows are tall. I'm modeling oceans. Yeah, that's right.
I have a question.
Yes.
Too. Thank you very much. The first question, you mentioned applications mostly to oceanography, or
yep.
But I guess mental convection is one. Did people look into it in mental convection also, or is it different?
No, that's a good question. We haven't thought about that at all. There's a whole separate community. I don't know to what extent they know anything about the mantle, as you say, which is often people argue about. Well, there's also convection in the core. People argue it's driven by compositional accretion at the boundaries, etc., etc. That becomes, I think, more similar to the kind of Rainey-Bernard stuff that I mentioned at the beginning, because people like Steve Tobias, these ideas about, you have to think about moisture and then you get condensation. So I don't think we're nowhere near thinking if that difference between the horizontal and the we haven't thought about that. That's a really interesting question.
And another one, in your extension, you mentioned rotation or spherical geometry.
Yeah.
And what you look at is essentially shear driven by the horizontal convection. I mean, it's the interaction of this shear with
that's right.
But of course, you have other ways of introducing shear in the ocean. For example, usually you can have horizontal convection, and you also can have wind.
That's right. Yes, that's right.
Drive the shear on top of it. So
that's
modify the base flow, taking into account the shear on top of it.
That's completely right. So I'm being a bit naughty here because, in the Earth context, clearly the issue is the mechanical forcing at the boundary. And in fact, there are papers by people like Bill who've looked at the competition between mechanical forcing and buoyancy forcing. And Katie's experiments were about that. There are many ways to bring shear into the problem. I mean, one of the reasons that rotation is so concerning is because it tries to suppress any kind of vertical motion, right? So then can you ever get Rayleigh-Bernard? There's a whole literature that I didn't mention. When I say rotation, it's because mathematically in this linear stability problem, you can put rotation in. You can write down the basic state, but we haven't done that yet. They're no longer polynomials, they're now exponential functions, but you can do it. There are many ways to get shear. This is a very nice self-consistent way of getting shear, but it's not the only way.
Thank you.
Thank you. So there is a question by Maurice.
Well, I have just a comment I agree that boundary conditions are quite important. In fluid mechanics, we know that. And I was wondering if anybody has done the following experiment. You take a Rayleigh-Bénard convection cell, but it's a torus.
Oh.
So you see, this way you remove the problem of the boundary conditions.
Yeah, so people have certainly done, there are these famous experiments by Reed and so on, the dishpan experiments, where you have a rotating tank and you have cold in the middle, warm on the outside, but it's a torus. Now, the experiment with the torus to avoid lateral boundaries, I don't know. That's a very interesting question. Probably someone has done it, but I don't know who. Yeah. That would then quantize your wave numbers, but assuming your torus was big enough that you could, probably been done, but I don't know by who. You can do it numerically. That's called periodic boundary.
So I have a sort of a less serious question. So what's the conclusion about Enceladus?
Okay, so that's a good question. So one thing we did, so of course Enceladus is way off all these diagrams. It's much more relevant to look at this picture. And in the first version that was submitted, we had a diagram, I should have copied it, which had, the various moons in the Earth, trying to guess where they were on this curve. Referees did not like that diagram, didn't like it very much at all, so we took it out. So I've forgotten what it was. It turned out the Earth was incredibly close to the boundary, but just on the correct side. It was actually horizontal, so that was good news. I'd have to look at the diagram. A lot of these moons were quite close to this line, but of course, since we're neglecting rotation, it's one thing to neglect, to idealize boundary conditions and so on. I can live with that. The rotation thing really worries me. I think until we do this with rotation, I'm very wary to try and guess where we are. But actually, one important thing, we have incredibly little data about Enceladus, right? I mean, we're told there are geysers, we're told there's a moon, we're told there's an ocean. We don't know. So it's really important to publish these papers now, before these experiments get to Enceladus and tell us what it's really like.
Yes, yes.
Absolutely. So this is the great time to write papers about Enceladus and Callisto and Io. You don't want to do it in 5 years' time. You'll have to match the data, which is terrible.
The SR probe is not planned before 2050, so it's still
But
time.
there's JUICE and, well, Enceladus, yeah, but the JUICE is going to be arriving in Jupiter in about 2030, and there's another one. So there are some going to Jupiter. So best to get your results in now. There are other exoplanets, of course. I don't know whether our data is enough. My impression, they're all, rocky Goldilocks things. I don't know if any look like that.
There is, for instance, Jovian.
There are Jovian type exoplanets, and maybe they got moons like this. So yeah, in that case, yeah, but then they'll tell us, oh, they must look like the ones in the solar system. Yeah, match those first. We'll see.
Any other questions? No other questions? Let's thank Stefan again.
Thank you.